Good morning to everyone. Can you hear me?
Good morning, madam. Yes.
Yes, madam.
Okay, I'm sorry for taking this much time. I'm sorry again. So let's start the session. Okay. So we were discussing on discrete probability distributions. Under that, we discussed discrete uniform distribution and Bernoulli and binomial. And we were discussing yesterday about the geometric distribution. In the geometric distribution also, we have Bernoulli trials. In advance to that, we continue the Bernoulli trial until the first success occurred, right? Until the first success is related to geometric. Rth success, that is where R is greater than 1, it is known as a negative binomial distribution. So we were discussing on geometric distribution. So here the random variable we are assigning is number of trials required for the first success. පළවෙනි success එක occur වෙන්න අපිට trials කීයක් කරන්න ඕන වෙනවද කියන එකයි random variable එක වෙන්නේ. So we define the probability distribution. So since the X trial is the first success, there should be X minus 1 trials that are failures. So we can build up the equation probability X equals X. That means probability of number of trials equals to X, which occurs the first success in the X trials is equals to the probability of success P into 1 minus P X minus 1, because 1 minus P is the probability of failure. So failure happens X minus 1 times. Therefore, the probability distribution is simply defined as P into 1 minus P to the power X minus 1 for X up to 1, 2, 3. So the mistakes, actually there are some mistakes in the previous note, so I have uploaded it again. So if you need it, you can replace the chapter 3 part 3 using the recently uploaded document, right? I corrected the mistakes I have done yesterday. So we discussed example there. And here also in the diagrammatic representation we discussed yesterday, it yesterday, but there I have input the cumulative frequency bar graph or the line graph. So actually using cumulative, it is not clear the idea what I wanted to tell you. So I put the cumulative one because the table gives us the cumulative value, but the idea is clear when this bar graph is presented. So in the geometric distribution, when the first trial is a success, can be calculated using this. So it is 0.4 into 0.6. 1 minus 1, it is 0. So the value is 0.4. So using bar graph, it is denoted here, right? And when X equals to 2, so it becomes 0.4 to the power, sorry, 0.4 into 0.4 into 0.6 to the power 2 minus 1 is 1, so it becomes 0.24. Likewise, we can calculate the probabilities where the first success occur, right? So then we can draw this line graph or the bar graph, right? So when we find in the mode, so mode is the most likely value to occur, right? So always the x value with the highest probability is the mode, most likely value. So here, always in the geometric series, it becomes 1. The mode becomes 1. That means x equals 1. Why? We know that when we increase the value of x, when we increase the value of x, the probability is decreasing, right? Probability is decreasing. It is clear in this graph as well. So always in the geometric distribution, mode is 1. So that is the idea I wanted to tell you, right? So there are some useful results of geometric distribution. There are two useful results. So we could use those two important results to calculate the probability values, right? So the first one is, if x is a geometric with the probability of success p, then probability the first success occur, the number of trials we want to do to obtain first success is greater than k is equals to q to the power k. You know that q is the probability of failure. It is 1 minus p, right? That means we have done k trials, but the first success did not occur. That is the meaning of that, right? We have done k successes, but till the kth success, there are no any till the kth trial, there are no any successes has been occurred, right? So that probability is equal to the q to the power k, where q is the 1 minus p, the probability of failure, right? So we can prove it. So probability of x greater than k, we could write it using the summation. So since it's greater than k, we sum up from the k plus 1 to infinity, k plus 1 to infinity, p into 1 minus p, x minus 1, right? So we can expand this. We can expand this. How we can expand this? We can substitute values k plus 1, k plus 2, k plus 3 up to infinity. So after expanding the equation, then we can use the summation of geometric series, right? In mathematics, you learn how to add up a series that follows a geometric series, right? So after expanding, then we can use the sum of geometric series. Right? After obtaining the sum of geometric series, we can obtain this expression. So it is 1 minus p into p to the power k into p divided by 1 minus p. So it is 1 minus p to the power k, 1 minus p is q, the probability of failure. So it is q plus k, right? So probability that the first success occur after the k trials is equals to q to the power k. So this is an important result. Okay, that is the first result we learn under the geometric distribution. Then the second result is no memory property. No memory property. So what is no memory property. If X is a geometric with P probability of success, then P probability, the first success do not occur. That means first success is beyond the J plus Kth trial, given that the first success do not happen after the Jth trial as well. It is the given information. So it is equals to the probability of first success occur beyond the Kth value. That means, so we can use this line to illustrate the thing I am going to say here. So here this is J. So that is the given information. Given information. See here the given information. The probability of first success is occur after J trial. එතකොට J වෙනකම්ම success එකක් වෙලා නැහැ. J trial is also a failure. Right? So it is the given information. When that information is given, probability that the first success is go beyond J plus K trial. So here also again a failure. So success is somewhere after the J plus K trial. Right? So the given information, the Jth trial is also a failure. Then what the probability, the J plus K trial up to J plus K trial do not have the first success is equal to probability the first success of occur after the Kth probability. That is an important result. So it is called no memory property. කියන්නේ යා memory එකක් තියාගන්නේ නැහැ ඊට කලින් successes or failures ගැන. Right? That is why it's called no memory property. So i.e. knowing that J trials have passed without a success does not affect the probability of K more trials being required for the first success. ඒ කියන්නේ මෙතන ඉඳලා මෙතෙන්ට එයාට success එකක් occur වුණාද කියන එක affect වෙන්නේ නැහැ. J ඉඳලා J plus K ට යනකම් මෙතන trials K number තියෙනවා. ඒකට effect එකක් නැහැ කියන එකයි මේ no memory property එකෙන් කියන්නේ. J ට කලින් success එකක් වුණාද නැද්ද කියන එක. ඒ කියන්නේ failure එකක් වුණා කියන එක බලපාන්නේ නැහැ. J ට පස්සේ success එකක් ආවද කියන එක තමයි no memory property එකෙන් කියන්නේ. Right? So we can prove it. How? So we know that this is a conditional probability value. A given that means a conditional probability. So we can write it as P x greater than J plus K intersection x greater than J. That means we take this part as A, this part as B. So we know that probability A given B could be written as probability A intersection B over probability B. Right? So this is the conditional probability. So using that conditional probability, we can write this, right? Then probability x greater than J plus K and x greater than J. So that is the intersection and this one, right? So greater than J plus K means from the J plus K to infinity, and greater than greater than J means from this point onwards, right? So the intersection is here, this one, right? Probability x greater than J plus K. So I think it's clear. We are taking the intersection. right? Then probability x greater than j plus k, using the first result. See, using the first result, we can write it as 1 minus p j plus k. Right? The first result gives us probability x greater than k equals to q to the power k. Right? See here? Yes. Then using that result, we can write this expression. We can that result to the this probability values. Then it is q is same as saying 1 minus p. So 1 minus p j plus k, 1 minus p to the power j plus k over 1 minus p j. Right? So j terms cancels out. Then the remaining is 1 minus p to the power k. So 1 minus p to the power k is, again applying this result, it is p x greater than k. Right? So those are the two important results we obtain through the geometric distribution. So we can use those two results to calculate probability values in a geometric distribution. Okay. Right. Is it clear? Any problems, any questions up to now? Okay. Let's go to the example. Okay. A coin is biased so that the probability of obtaining head is 0.6. If x is a random variable that the number of tosses required to get the first head, find probability x less than or equals to 4, probability x greater than 5, the probability that more than 8 tosses will be required to obtain head, given that more than 5 tosses are required. So here a coin is, it's called coin is biased. Then obtaining head, the probability of obtaining head is not 0.5 here, it is given as 0.6. So x, the random variable assigned as the number of tosses required to get the first head. So getting head is a success. We can take the getting head is as a success. And it's a Bernoulli trial, we know. So the Bernoulli trials continue until the first success occurs. So it is a geometric distribution with the probability of success 0.6. Right? Okay. So now we have to find what is P probability x greater than or equal to 4. Okay, just try the example. Take time and try.
Yeah, well,
So here we can use the summation because we want probability where x less than or equal to 4. That means summation x goes from 1 to 4. The distribution is p into 1 minus p x minus 1. So this is same as writing you can use either that equation, or this is same as writing the probability of 1 minus the probability of x greater than 4. Okay. So according to the result, 1, it can be written as 1 minus p to the power 4. It is 1 minus p is 0.4 to the power 4. Then the next one, using the result 1 again, you can write it as 1 minus p to the power 5. So just 0.4 to the power 5. So the probability of first success, so part C is probability that more than 8 tosses will be required to obtain head, given that more than 5 tosses are required. So given information is to obtain the first success, 5 tosses are required, more than 5 tosses. So it is the given information, and we have to find that the probability it take more than 8 tosses to obtain the first success, to obtain the head, right? So it is the probability x greater than 8, given that x greater than 5. So here 8 is 5 plus 3, right? So k is 3. So just we can write this as probability x greater than 3. එකට පහට කලින් success failures ඔක්කො වුණා කියන එක අපි consider කරන්නේ නැහැ. It is called the non-memory property, the second results obtained through the geometric distribution. So using again the first results, we can write this as the probability of failure to power 3. Okay, someone has asked me to explain the part C again. So the probability that more than 8 tosses will be required to obtain head, given that more than 5 tosses are required. We can first success එක එන්න process 8කට වඩා කියන්නේ trials 8කට වඩා ඕන වෙන probability එක මොකක්ද? information එකක් දීලා තියෙනවා given that it takes more than 5 processes to obtain the first success. ඒ කියන්නේ success 5ක් වෙන්න, ඒ කියන්නේ success trials පස්වෙනි trial එක වෙනකොට first success එක ඔක්ක වෙලා නැහැ කියලා දීලා තියෙනවා නම් පළවෙනි success එක ඔක්ක වෙන්න process 8කටත් වඩා යන probability එකයි අහන්නේ. Right? So the probability that more than 8 processes will be required is probability x greater than 8. Right? So the probability, obtain a head given that more than 5 processes are required කියලා කියන්නේ first success x greater than 5. So it is the given information. Given information is written as a conditional probability. Right? So using the no memory property, here is the 5 and here is the 8. So we take this as j, we take this as j plus k. So here k is 3. So according to no memory property, this is equals to x, probability of x greater than k. So here k is 3. And we can calculate the probability. The first success occur the first success if it take more than 3 trials. I think now it's clear. Okay. So as we found mean, variance, and the moment generating function, the three important properties in earlier distributions, here also we are finding mean, variance, and the moment generating function, right? So first we are finding the mean. So mean we can write using the expression summation x goes from 1 to infinity, x into the distribution, x into the probability distribution, that is p into 1 minus p to the power x minus 1. So after expanding it, that means we substitute values from 1. So if x equals to 1, the expressions become p. If we substitute the value 2, it becomes 2p into 1 minus p. Likewise, we can expand this equation, right? So after expanding, we can take p out, and the remaining part is 1 plus, in place of 1 minus p, we replace it using q. It's same, right? So p into 1 plus 2q plus 3q squared. Likewise, we can write the series. Okay, so we can write the summation of that series. You can use the knowledge of summing the series. Here we can write the mean as p over 1 minus q squared, right? So 1 minus q is again p. So 1p is cancels out, and the mean can be written as 1 over p. So that is the mean of the geometric distribution. Next one, the variance. Variance can be written as expected value of x squared minus expected value of x, the whole thing squared. So we earlier found the mean expected value of x. Then we want to find expected value of x squared. So using the expression, we can write expected value of x squared as summation x squared into the probability distribution p into 1 minus q to the power x minus 1. So as earlier, we can expand it by substituting values from 1 to infinity. Then we can take 1p out and write the remaining terms using the q, probability of failure, right? Then we are dividing the series into two series to make the calculation easier. So there are some non-series. We can obtain the summation, right? There are some non-series. So we have to make our series to those non-series to obtain the summation. That's why the series is going to separate into two series here. Okay, so we separate the first series into two series. 1 here, 1, and we take 2q here and 3q, and the remaining 6q is here. Here the 4q, only 2q is taken here, and the remaining part is here, right? In the 16q cube, we only take 4q cube here, and the remaining part goes there, right? So now we can write the first series. We can write the first series. It is, the summation is 1 over 1 minus q square. It's expected value හොයන්නත් ගත්තේ මේ series එකම තමයි. මේ summation equation එකම තමයි, right? Okay, then from the second part of the series, we take 2q out and write it as 1 plus 3q, 6q squared, 10q cube, like that, right? So we can write that equation, that series, as this series, right? The summation of that series is 1 over 1 minus q to the power 3 or cube. So substituting the summation of those series, finally we could obtain the expected value of x squared is 1 plus cube over p squared. So by substituting that expression here, and we can obtain the variance. It is q over p squared. Okay, then the moment generating function. It is the expected value of e to the power tx. So as earlier, we can write it using the expression, the summation e to the power tx into the distribution. And by expanding and using the knowledge of summation of a series, finally we ended up with this equation, right? You have the notes, so just go through it. It's easier to understand. Okay, next consider this example. The probability that a marksman hits a bird is 0.4. Each attempt is independent from all others. Find the probability that he hits the bird for the first time on his fourth attempt. The mean number of throws needed to hit the bird and standard deviation, the most likely number of throws until he hits the bird. Okay, I'll give you 5 minutes. You can use the results you obtain through the mean variance and moment generating function is straightforward. So its moment generating function is not needed to actually to calculate to solve this example. So using the results we used under the geometric distribution, please do this example. I'll give you 5 minutes. send me your answers. Okay, these are the answers. So part C, in part C, the most likely number of throws until he hits the bird. The most likely number of throws means the mode. So the mode is always 1. So most of you have sent the answer to part C 0.4. That is the probability, right? So most likely number of throws they are asking. That means number of trials. So that is 1. Not 0.4. It is probability of success. Or the probability of obtaining the first success in the first throw. That is the probability. So the highest probability value, the number of trials that having the highest probability value is the mode. So 1 is the mode. So for any geometric distribution, the mode is 1. Okay. Right. So that is the geometric distribution. So in the geometric distribution, we are concerning about the number of trials to obtain the first success. So next is negative binomial distribution. We call it as a binomial waiting time distribution as well. So here we are concerning number of trials required to obtain R successes. So we want to count R number of successes, not the first success. We want R successes. So how many number of trials required to obtain the R success? Right? So here first trial could be success or failure, second trial success or failure, third one likewise it could be a success or failure, right? But when the X trial happens, here, the X trial should have the R success. Right? So how many number of trials will it take to obtain the R success? So that random variable follows a negative binomial distribution. In earlier case, in the geometric, right, till the X success, X trial is the first success. But here, the X trial is the Rth success. So we are finding to obtain R number of successes, how many trials we should do. Right? That is the number of trials required to obtain R successes. So it follows a negative binomial distribution. Right? In the binomial distribution, we know that number of number of trials is fixed. But here, the negative binomial distribution, number of trials are not fixed. We are finding what is the number of trials to occur the Rth success. In the binomial distribution, we fix the number of we fix the number of trials, and out of those trials, how many successes have been occurred is the concern. Right? So here we are given that Rth successes have occurred, but how many trials should we need to obtain that Rth success? So it is the reverse of the binomial distribution. In the binomial distribution, we are finding with the fixed number of trials, how many successes are there. In the negative binomial distribution, we find with the successes are given, number of successes are given. We want to find how many number of trials are required to obtain the number of successes given. Right? So that is the difference of negative binomial and binomial distribution. So for the event x equal x to occur, one must obtain r minus 1 successes in the first x minus 1 trials in any order, and then obtain a success in x trial. That means, so this is x and this is x minus 1 trial. Right? So from first trial to x minus trials, from first trial to the x minus 1th trial, there should be r minus 1 successes. Then only the when x trial is a success, it becomes r successes. So within x minus 1 trials, there should be r minus 1 successes in any order. ඕනම order එකකින් වෙන්න පුළුවන්. ඒ කියන්නේ පළවෙනි එක success වෙලා, දෙවෙනි එක fail වෙලා, තුන්වෙනි එක success වෙලා, ඒ විදිහට වෙන්නත් පුළුවන්. මුල්ම r minus 1 observations ටික success වෙලා ඉතුරු ඒවා failure වෙන්න පුළුවන්. ඉතින් ඕනම order එකකින්, but somehow at the end of the day, within the x minus 1 trials, there should be r minus 1 successes. Right? So we can write the probability of occurring r minus 1 successes in x minus 1 trials using x minus 1 c r minus 1. And the probability of success p to the power r minus 1, because there are r minus 1 number of successes, and failures, how many failures? X minus 1 minus r minus 1. So it is x minus 1. So it becomes 1 minus p into x minus r. Right? So I think it's clear now. Okay. So the number of ways we can obtain r minus 1 successes out of x minus 1. It is given using x minus 1 c r minus 1, and within that x minus 1 trials, there are r minus successes, r minus 1 successes. So it is p to the power r minus 1, and within that x minus 1 trials, there are x minus 1 x minus 1 minus r minus 1 failures. So it is x minus r. So there are failures 1 minus p to the power x minus r. Right? So the probability of occurring r success in the x trial is p. And finally, probability of occurring r success in x trials is this one. X minus 1 c r minus 1 to the power 2 p to the power r should be r minus 1 actually, I guess. No, we have to multiply it by p because probability of occurring r success in the x trial, right? So this is probability of occurring r minus 1 successes in x minus 1 trials, but we have to multiply it by the x trial as well. occurring the X trial, it has P probability. So we have to multiply this by P. So probability of occurring R success in X trials could be written as X minus 1 CR minus 1 P to the power. Now it's not R minus 1, it's P, because we consider the last trial, the X trial. It has a success. The X trial is a success. Therefore, the earlier expression should be multiplied by P, and now it becomes not PR minus 1, PR. Right? Is it clear now? Any problem? Okay. Any problem? I guess no, right? If you have any, please ask me. Okay, then we can write it as a definition now. A random variable X has a negative binomial distribution, and it is referred to as a negative binomial random variable if and only if the probability X equals X. That means probability, the R success, there are R success in X trials. That means we need X trials to obtain R success, that is equals to X minus 1C R minus 1 into P to the power R into 1 minus P to the power X minus R, where X is R, R plus 1, R plus 2. So here X is number of trials required to obtain R successes, and P is the probability of success in each trial. So using the notation, we are writing X follows negative binomial. In B, we should include the parameters R, P. R, P. R is the number of successes. P is the probability of success in each trial. So if you can remember, we write the geometric series using GEO within the brackets probability. Why? We know that the number of trials are not fixed, and we know that we are finding the success occurring first trial. So that's why we are not including the number of trials there. And the binomial, in the binomial, we denote it as bin N, P. N is number of trials. The number of trials are fixed, and then the probability of success in each trial. So here, in the notation, the parameters are R and P. R is the number of successes. Okay. So using the knowledge you have now, I think you can do this exercise. Prove that mean, variance, and moment generating function are those things. So it is easy because you proved the geometric one earlier. So only difference is mean is multiplied by R. Variance is also multiplied by R. And moment generating function a rth power is added. That is the only difference, right? So try to prove it at your own. Okay. It's not that much difficult. You can do it your own. Okay, now consider the example. If the probability is 0.4 that a child exposed to a certain contagious disease will catch it, what is the probability that 10 child exposed to the disease will be the third to catch it? Right? So the probability of catching the disease when a child exposed to a certain disease is 0.4. Again, disease එකට expose වුණ ළමයෙක්ම ඒ disease එක හැදෙන probability එක දීලා තියෙනවා 0.4 කියලා. Right? Suppose the contagious disease is coronavirus, right? So if we have exposed to someone or if we have close contact with a person having a coronavirus, then we can't say that we got the disease. අපිට disease එක එන්නත් පුළුවන් නොඑන්නත් පුළුවන්. So disease එක එන්න probability එක 0.4. Right? That means if we take the catching the disease as a success, the probability of success is 0.4. And the problem they're asking is, what is the probability that the 10th child exposed to disease will be the third to catch it? 10 වෙනියට expose වෙන ළමයා කියන්නේ ලෙඩේ හැදිච්ච 3 වෙනි ළමයා වෙන probability එක. So there are 10 child, right? So if we consider here 9th child, the first child could be success or failure. Second child also could be success or failure. Third child until the 9th child, how many successes are there? Only 2. Only 2 successes. Only 2 successes are there up to 9th child. And the 10th child is definitely a success. This child, the 10th child is a success one. He catches the disease. So when it comes to 10th child, number of successes should be 3. So we are asking, what is the probability of being that? What is the probability of the 10th child exposed to the disease will be the third to catch it? So it is a negative binomial distribution. Right? So in the exams, this is important to understand this concept. Why? In the exams, you are not given this follows this distribution. Right? Looking at the problem, only you can identify what is the distribution underlying this question. So first understand the question and you can match the problem with the probability distributions you learn. So this is not a binomial distribution. Will be the third කියලා අහනකොට ඒක binomial එකක් නෙමෙයි. එහෙනම් binomial ගැන අහනවා නම් කොහමද අහන්නේ? ළමයි 10 දෙනෙක්ගෙන් 3 දෙනෙක් disease එක හැදෙන probability එක 10 දෙනාගෙන් 3 දෙනෙක්. එතනදි කියන්නේ 10 වෙනියා තමයි 3 වෙනියා කියලා. binomial එකේදී. හැබැයි negative binomial එකේදී අපි කියන්නේ ඒ කියන්නේ 3 දෙනෙක් හම්බ වෙන්න disease එක හැදිච්ච 3 දෙනෙක් හම්බ වෙන්න expose වෙච්ච 10 දෙනෙක් test කරන්න වුණා. So 10th child is a success. ඒක මෙන්න මේ problem එකේදී important property එකක් වෙනවා. So it is a negative binomial distribution, right? So let success catching the disease, then P equals 0.4. So let X number of children exposed to the disease whom our child have caught it. Right? So we are asking the probability X equals 10 here. What is the probability X equals 10? Okay, so this is the negative binomial expression. So we are asking X equals 10. Third child have caught it. So the third child is the 10th child exposed to the disease. Right? So it is equals to 9C 2 and probability of success 0.4 to the power 10 and 0.6 7. No, there is a mistake, right? This is not X, actually, this is R, isn't it? This is R. What is the answer? Okay, next problem. Team A plays against Team B in 7-game World Series. That is, the series is over when either teams win 4 games. For each game, the probability of A wins is 0.6 and the games are assumed to be independent. What is the probability that the series will end exactly, right? Exactly 6 games. So, we want to find the probability that the series will end exactly 6 games. Right? So, here we have 2 cases. Right? So, when we write the probability, the series end in 6 games. Either team A could win 4 games in 6 games, or team B could win 4 games out of 6 games. Isn't it? So when to series end in exactly 6 games, right? Team A could win 4 games in 6 games. Games hiking 4ක් A team එක දිනන්න පුළුවන්. එහෙම නැත්නම් games hiking 4ක් team B එක දිනන්න පුළුවන්. There are 2 ways. So probability of series ends in 6 games is equals to probability of team A wins 4 games out of 6 games, or team B wins 4 games out of 6 games. So the games are independent. We could write the O here as a summation. Probability of A wins in 6 games and probability B wins in 6 games. Right? So considering the first one, probability of A wins in 6 games. Right? So we know that probability of winning the A team equals 0.6. Right? So hiking game එක ඉවර වෙනවා. Games hiking game එක ඉවර වෙනවා. A team එකේ එක success වුණොත් 6 වෙනි trial එකේදී 6 වෙනි game එකේදී. Team A consider කරොත්. Right? ඒ වගේම අපි team B consider කරොත් team B consider කරොත් team B එකත් එයාගේ 4th win එක ගත්තොත් 6 වෙනි game එකේදී again the team B win. Right? So within the first 5 games, then there should be 3 wins. Right? So considering the team A wins, the scenario is follows a negative binomial distribution. Right? If we consider the random variable x as number of games played of which team A has won r times, r is now 4 and p is 0.6. So it is a negative binomial distribution. Right? So we can find the probability where the number of success equals to, number of trials equals to 6 to obtain the 4th success in the 6th trial. So it is a negative binomial distribution. Right? So now we can write Px equals 6 as x minus 1 is 5, 5c, r minus 1 is 3. 5c3 into, here again it should be r, right? Not x. 0.6 to the power R is 4 and 1 minus B is 0.4. X minus R is 6 minus 4, it is 2. Right? So similarly, we can obtain the number of games played of which team B win in our time as Y. If we take it as a random variable Y, we want to find Y equals 6. That means the probability it takes 6 trials to obtain the 4th win. Okay, so it is 5C3 again. Right? But now probability of team B wins is the success case we consider here. So P here is 0.4. 0.4 to the power 4 and 0.6 to the power 2. Now we can add the two probability values and find series goes for 6 games. Okay. You can now take your time and try the third example. There are some missing informations here. Wait. Okay, can you see this example?
Yes, madam.
Okay, this one is the third one, right? So make the corrections to your note. Send me your answers once you finished. Ayush, your part A is correct. Ayush, part C also correct. Check the part 2. I guess the first two digits are correct. Check the calculations in part B. And 261. Your part A is correct, part 2 is not. Okay, answers should be, I'll give you answers. For part A, it should be 0.00729. And for part B, 0.99144. And for part 3, 0.271. Okay, try to obtain these answers. Right. Okay. Try to obtain those answers if there is any. So if there is any correction to be made, let me know, right? These are the answers I got. Okay. So that is the end of the distribution negative binomial. So far under discrete distributions, we discussed 5 distributions: discrete uniform distribution, then the Bernoulli distribution, and binomial, geometric distribution, and negative binomial. So we have to discuss another 2 distributions under the discrete uniform discrete distributions, and then we can move on to the next chapter, continuous probability distributions. So we are about to discuss another 2 distributions. Those are called hypergeometric distribution and Poisson distribution. So let's continue the discrete distributions from next week onward. So if you have any questions, you can ask now. Okay, if you have no any questions, let's continue on next Monday, right? So I think a tutorial has been uploaded. So do it and submit. Submit your tutorials on time, so you can obtain marks through the tutorials, and it's very much important. So that is all for today. So thank you for joining.
Thank you, madam.
Thank you, ma'am.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
You are welcome.
Thank you, madam.